Hello everyone. As usual, quick video, this time recapping the information we talked about for the Internet Protocol, not the Internet forwarding, but the Internet Protocol. Let's start by taking a look at the book chapter in the table of contents. Okay, enlarge that a little bit more. There we go. Come on, there we go. So, as far as reading for chapter 5, which is where this is located, obviously read the chapter intro and the introduction. You want to read the header fields section, both the intro and then 521, the IP header fields description. That's kind of the listing. That's what I do in the balance of this video. I apologize for my dry throat. I don't know what just happened. You can safely ignore the internet checksum. It's a pretty technical section, well beyond what we need, other than what you read in the header fields description. Same thing for the DS and ECN fields. It's not that they're not important, but they're sort of secondary and not in super wide use. I'm really torn about 524, the IP options section. I think what I'm going to suggest is kind of read the first little bit of it to understand what IP options actually are, because it's an important concept. Most protocols have some way built in to expand the protocol. So you basically sort of figure out these are the things we want our protocol to do, and then later on decided, wouldn't it be nice if we did this other thing as well? And with some sort of a mechanism for options or extensions, you can add stuff later without redoing the entire specification. So understanding what these things are, why they exist or existed, maybe is a better term, is actually really good. Because we'll see this in many other protocols as well. The reason I'm torn is that if you skim that section, you get to a table that says, here are all the options that are currently defined as standards, and it lists every one of them is either listed as we don't use this anymore, or as it is very rarely used. So it's one of those things where it's nice to have, but for a bunch of different reasons, which we can talk about in class, mostly having to do with security, most of these options were nice at some point, but they're just not being used right now. So it's kind of the same thing that IPv6 is also extendable. It uses a different mechanism. In this case, they're called extensions rather than options. And so in the extension headers, and so in the IPv6 section, IPv6 extension headers, just read the first little bit of the intro section, just so you can sort of understand what these things are. And again, we'll talk in class a little bit about what what you might be able to do with these. We'll actually loop back to this. There's one area, mobile IP, where some of these extensions are actually in use. But again, even in IPv6, there are some significant hurdles, I guess, to using extensions, because a lot of them, if not everybody agrees that they're going to use them, aren't very useful, and so these things are used in very narrow cases. So if if you ask what you to take out of that part of the chapter, it's not the specific options or the specific extensions, but understand why they exist and how they're implemented, so that if something came up next year or saying, wouldn't it be great if we could do this, the mechanism exists to add whatever this is to IP 4 or 6, assuming the standards community agrees. So knowing that that capability exists is very fundamental. But as it turns out, right now, the base protocols actually serve us really well, and the options and/or extensions really are used in very rare, only in very rare circumstances. Then finally. And this is really looking ahead, so I'm going to do a separate video on this. But as you're reading, understand that so the other big topic we're going to go into is going to be IP forwarding, right? So far we've been talking about the structure of the IP protocol and the IP header. The rest of our discussion of IP will center around how do we actually use IP to get a packet from where it started to where it has to go. And that's called IP forwarding. So that section 5.4, you need to put on your radar screen. We have not talked about it yet, but if you're gonna start reading ahead, that will be the thing to do. So again, just a quick recap. 5.1 introduction, yes. 5.2 through 5.2 and 5.2.1, yes. Then skip everything. Then skip 5.2.2 and 5.2.3. Read a little bit into 5.2.4 just so you know what these things are. Read a little bit into 5.3, just sort of the intro to know what these things are. And that will get you caught up to the week that's just ended. And then plan on reading all of 5.4 along with our class discussions next week. We will do mobile IP at some point, much later in the semester. It's a much more specialized discussion, and I'm going to set that aside, and we will not cover any of the other parts of chapter 5. So there's your kind of your summary of reading assignments. What I did in class, and what I want to utilize again here, is just a capture of a packet, just to kind of highlight some of the bits and pieces of the IP protocol. Just a quick recap. So this is Wireshark, and I did on purpose include the Ethernet section. So a quick reminder: Ethernet addresses are 48 bits, or 6 groups of 2 hexadecimal digits each, 6 octets. And the first half of them are vendor assigned, so they identify the vendor, which I let Wireshark substitute for us here. Again, important: the Ethernet header keeps track of what the payload is. So by looking at the Ethernet header, we know that the payload of the Ethernet packet is an IPv4 packet. Right. So now we get to IPv4, and you can sort of see Wireshark in its summary basically says, well, the things that you probably want to know the most is that this is IPv4, that the source address is 10.0.0.3 and the destination is 10.0.0.254. Those are both addresses in my home network. All right, so let's go through the IP header a little bit. So fortunately, because we are actually running 2 different versions of IP, fortunately the IP protocol has a mechanism for identifying what version of IP we're looking at. So this is IP version 4. The first header is set to 4. And obviously would be set to 6 for IPv6. The header itself is 20 bytes long. So that allows the receiver of this packet to efficiently identify the information it needs to process before it gets to the payload. These are the then that's followed by the two fields that essentially have. Oops, didn't want to highlight the length. So these two fields, DSCP and ECN, both have to do with, one of them has to do with class of service, it has to do with sort of prioritized traffic, and the other one, ECN, has to do with reacting to congestion in as efficient a way as possible. Again, it gets very detailed and not used that often. So we're going to skip over that for now, but understand that there are some mechanisms here in certain applications. I can take advantage of these to control a little bit better how traffic is handled, and we'll talk more about them when we talk about IP forwarding. The next field tells us that the total length of the packet. So this is the payload of the Ethernet packet, right? So this is the total IP packet. It tells us that that packet is 84 bytes long, so 64 bytes of IP payload and 20 bytes of header information. Let me say a few things about fragmentation. I'm going to talk more about that once we actually start talking about forwarding, because this sort of happens during that process. Whoops, I didn't want to do that. So there are a couple of different header pieces that are all sort of tied together and refer and relate to this concept of fragmentation. So this packet is pretty small. It's 84 bytes total. But what if this packet was bigger, but small enough to be able to just be transmitted on the originating network just fine, but then somewhere along the way, some router is saying, well, I received this packet, but the network I need to send it out on has a different maximum length, and so I can't send it. What do I do now? And IPv4 allows something called fragmentation. And we need to talk about that in a bit more detail. I don't want to do that necessarily in the video, but essentially, if you allow this, then what that says is the router that had this problem, that the packet showed up but it's too long for the outbound path, is then allowed to basically cut it in half or whatever it needs to do to create multiple IP packets that are small enough to be transmitted. Now you have a problem where we sent a single IP packet, but now past that router, it's really 3 different packets that all represent different parts of the original packet. So to help with putting that all back together, there's an identification number in the packet, so that it's a bit easier to tell that oh yeah, these two packets, these two fragments have the same identification number, so they must belong together. There's this fragment offset field that basically tells me this is the first or the third or the fifth or whatever piece that this thing was cut up into, so the receiver can put it back together properly. And then in this case, there's basically just some processing control flags, some instructions on downstream router saying, here's what you should do. And this one is set to say, I don't care what it is. If you can't transmit it, just delete it. And it generate an error message in most cases. But basically, so this particular packet is set up so that if a router were to receive it and say, oh, I need to cut this in multiple pieces, it'll look at this flag and say, oh, I'm not allowed to do that. And it will just delete the packet. That packet would never arrive under that circumstance. All right. We talked about in class about the time to live field. So this packet has 63 more hops to go. Right, so the next router that sees this packet and forwards it will subtract 1, so the packet will have a 62 time to live entry, and the next router will subtract 1, will be 61, and so on. If it ever were to reach 0, the packet would be deleted. So that prevents if there's a routing problem and packets basically going around in an endless circle, after a while they just get deleted and don't overload the network. Just like in Ethernet, the IP header contains an identifier. It tells me what the IP payload is. In this case, it's ICMP, which is one of the control protocols, sort of internal management protocols. And then the last thing is a checksum that basically is used to verify that the header information wasn't corrupted, so that we're not sending something to the wrong address just because a digit got flipped in transit. All right. And then, of course, I didn't expand the payload. We'll talk about ICMP in a future topic. So then the this internet packet, then IP packet, then contains as its payload the ICMP information, which I did not expand here. All right. So the takeaway from this part is, and I really want you to look at this in conjunction. So each protocol has basic control information. Ethernet and IP are the two we've looked at so far. That precedes typically, and in the case of Ethernet, there's one field behind it, but generally there's a header information that precedes the payload that helps in processing the payload, and the protocols are nested inside each other. So the Ethernet payload is the IP packet, the IP payload is the ICMP message in this case, but it could be a TCP packet or a UDP packet, which will both be topics down the road for us. So in terms of large concepts, that's what you want to take away from this, is sort of the overall structure of a nested protocol, where a packet contains a protocol inside a protocol inside a protocol inside a protocol, and then the details that you do need to be able to identify are, what's in an Ethernet header from a couple weeks ago, and now what is in what is that information that's stored in the IP header ahead of the IP payload. So hopefully that hope that helps, and I will see you in the next video.